Okay, so for our final event for today, we actually have a very special treat, a fireside chat with Will and Yi, chatting with Drew Baglino of Tesla. Please come on the stage.
Well, let you sit in the middle.
You can sit in the middle, yeah.
Okay.
Perfect. Hot seat.
There's a lot of lithium in those wells, too. For real.
Well, while Drew is sitting down, let me do a very brief introduction. Maybe a little bit longer introduction than a brief. 2005, when I joined in faculty, I think that was the time you probably just graduated from Stanford. So we probably didn't have overlap. So I come to Stanford, I didn't know, what are the most exciting energy problems I wanted to work on. At the time, people are looking at fuel cells. But somehow, I started to work on batteries.
Lucky you.
I didn't know I was lucky. I almost, my lab almost died because of just no funding to support battery research back in 2005 to 2007. I still remember the time I published the first paper. I think Ilan, JB, you're probably in the team also come to Stanford. We have a meeting. That was a big encouragement for me to start working on batteries. I say, wow, that sounds very important. First time to see the roaster. You probably participate in the design of the roaster, right? The first one. Very impressive. So, things fast forward now, 17, 18 years later, you come to bubble up, become the leadership position in Tesla. It's taking care of powertrain, energy. I'm so glad to see you're taking this leadership. This gave me a lot of comfort. So I've been driving my third Tesla right now. So last month, I just got delivered my third Tesla.
Awesome.
Driving experience just getting better and better and better. I like the wheel. That wheel had almost like driving airplane or the race car. Yeah, it's just amazing. So we start the short introduction. Let's welcome Drew to the stage. You're sitting right here. Let's give a round of applause.
So maybe I'll add also a sort of a funny note. I met Drew a few years ago, but it wasn't through a formal interaction. And I was actually just at my son's friend's birthday party.
Chuck E. Cheese.
At Chuck E. Cheese. And I said, this guy looks very familiar. And better find out who he is right away. So I think it really speaks to the power of Silicon Valley and just co-location. I think it was in Redwood City, and just that's those encounters.
That was the first time I've ever been, and last time I've ever been to a Chuck E. Cheese. I got to meet you.
We can go again.
Yeah. Yeah. For those who don't know, Chuck E. Cheese is a kids' pizza place with a lot of games. So.
Yeah, my boys in high school right now. I no longer go there. So. So, Drew, today is Fireside Chat, very relaxed. We just want to learn about what's exciting in your brain. You want to share with people.
Yeah, turning oil wells into energy storage, that sounds exciting. Yeah, or lithium wells is another exciting thing to use those oil brines for. But yeah, there's an immense amount of exciting things in this space right now. I think that the public psyche is 100% behind electrifying everything, which is fantastic. If you rewind to when I was at Stanford with Holmes, who I see in the audience, haven't seen in a long time, great to see you, Holmes, and others. And before you were here, I remember before this building was built, going to all of these, talks about, when's peak oil? When's peak oil? Is it 2009? Is it 2020? Is it 2030? Is it never? And I think it seems likely that peak oil is sort of near now, not because we're going to run out of oil, which didn't end up being correct, but because there's just a better alternative. And that's eventually going to be true of gas too, not because we're going to run out of gas, but because we're going to decide, hey, maybe we should use gas for really useful things that only gas can be used for, instead of heating people's homes and other things and businesses and industry and industrial processes. So it definitely is a very exciting time for that reason, that the public psyche about electrifying everything and like solving the climate crisis and electric can be better is coming around. Now there's still a lot more to do, especially in the building space, to like facilitize the electrifying of everything. In the utility space, especially with rules and the various regulatory structures to like enable the full capability of storage of any kind. Doesn't matter whether it's a concrete in an oil well or air in a cavern or lithium-ion battery intercalating between a cathode and an anode. Like none of those storage mechanisms are really being fully tapped with the current regulatory structures. So there's more to do, but there's a ton of momentum, which is exciting.
Yeah, that's great. So today we have the full day focusing on energy storage, particularly on batteries. So one thing we discussed a little bit in the morning is about scaling.
Yeah.
Tesla really coming up with the gigafactory concept. And now you see so many battery companies say gigafactory. So I did a little bit of calculation this morning. I say, wow, we will need to build about ranging from a few hundred, let's take it 300 to 500 terawatt hour batteries to power the car, if you use that for electrical grid, certain duration of storage.
Yep.
So what's your thought on the scaling issue?
Yeah, I think we are at that point where the exponential growth curve becomes really painful. When you're talking about something that you make 5 of, making 10 of it the next year, that's easy. And then maybe 20 of it the next year is also easy. But when you're going from making millions, like Tesla did 1 million last year, to 2 million, and everybody in the industry is trying to double in that way, it does really become a scale problem. If we stay on pace, which we're currently at, like as an industry of growing 50% year on year, it does seem possible that within 20 years, the 300 to 500 terawatt hours of batteries will be built. It's kind of nutty. It means we need to get the global annual production capacity of batteries to like between 15 and 20 terawatt hours a year, which is crazy. We're barely at a gigawatt hour now, and not really at a gigawatt hour. There's a lot of like inflated numbers versus what was actually produced. So it's massive growth, and the difference between like, I don't know, growing iPhones by 50% a year and a car battery or grid storage at 50% a year should be obvious to all of you. Like there's a lot more mass in a car than in a phone, and that mass has to come from somewhere. So ultimately that mass, largely the cathode, largely our highly refined transition metal, needs to come out of the ground, and with the like ore ratios that exist of 100 to 1 or 50 to 1 if you're lucky. Maybe you can get 20 to 1 depending on the resource. If you go to manganese, maybe you can get 10 to 1 or 5 to 1. It's still a lot of earth that needs to be moved at least once to get that 300 to 500 terawatt hours out of the ground. And that is a big challenge in front of us. Is for a while the battery industry could scale within the constraints of the entire economy that exists of materials and of refining and of chemical production and everything. But we're not really there anymore. We need to invest in our own everything, which is an opportune time when you're investing in your own everything to reevaluate what you're investing in. To date, the battery industry has been on the coattails of everybody else. So nothing has been like deliberately built for it. Mm-hmm. Full supply chain, that is true. Like the electrolyte is being built at some oil refinery that's doing a whole bunch of other petrochemicals, and like the electrolyte is a side business, and honestly, it's kind of annoying. The graphite historically also has been coming out of some petrochemical process, or maybe some coal mine kind of thing, but has again been sort of a secondary thing that they could make some money on. There hasn't been a lot of like dedicated investment in specific battery materials and refining processes, and that is changing, which is great. It's a big opportunity for a lot of different players to dedicate their mental efforts towards something that is needed to achieve this scaling. On the battery making side, specific to battery making, like the cathode synthesis or how electrodes are made or cells are assembled and battery packs are made, Sure, there's been bespoke investment. It's a bunch of unique stuff. But even that is not scalable like it needs to be to go to the huge multiple we're talking about.
Yeah.
Drew, maybe let me build off on that a little bit.
Yeah.
So, as we talked about before, this 300 or 500 terawatt hour of batteries,
Yeah.
most of it hasn't been built yet, and the factories to build them have not been built yet.
Yeah.
So, and we're only at a single digit terawatt hour today.
Yep.
And I think this could imply there's a lot of options and room for innovation. So, we hear a lot about sort of this cookie cutter situation of let's just keep building more of the same gigafactories. Sort of in your leadership of Tesla, how do you see this scaling, just being, as you mentioned, pragmatic and scaling up, but also constantly looking out for ways to improve? Can you maybe comment on a couple of exciting directions you're thinking, how you can change the next set of factories you build?
Yeah.
Mining processes.
Sure. I mean, I think the kinds of stuff that we've been focused on within the scope that we've taken on to date, which has been kind of like cathode and up, we've really been thinking about the typical things that you think about when you're making bread. Like the last bread factory could do 1,000 loaves an hour. I want the next bread factory to do 5,000 loaves an hour. Like, what do I do? Do I like change the chemistry and like a little bit more baking soda, a little bit more magic pixie dust, and it just rises faster? Or do I get a bigger oven? Or is my mixing going from like 1,000 liters to 10,000 liters? Is that how I make 5,000 loaves versus 1,000? That's kind of like things manufacturing engineers have done for a while, and we're doing that with the bigger form factor cell and the more efficient assembly lines and the slightly different electrode processing that we're doing. That's all about how do I make that same factory do 5,000 loaves an hour, same footprint or smaller, do 5 times to 10 times more than it did before. But that isn't the fundamental bottleneck of the next 10 to 20 years of battery growth. It really is the raw materials because, as I said, we've been in the coattails of everybody else's raw materials industry, and we haven't built our own. So, okay, what do we do there? Where are the big fulcrum levers to, that academia and other researchers that, everywhere can enable us to scale faster? So the biggest risk area at the moment, again, I mentioned lithium like 3 times already, is really lithium. So how can academia help? There's tons of ways, like better ways to do direct lithium extraction out of brines, out of various different types of ways in which lithium ends up in water, like in the salars and other things like that. More extensible resins for things like ion exchange membranes for getting lithium purified. Frankly, I mentioned it, I'll mention it again, like oil-field lithium, there's a ton of lithium in oils. There's lots of ways to like rethink the lithium problem and remove fossil fuel inputs into the lithium refining process, find ways to actually sequester CO2 in the lithium extraction process. There's tons of stuff that's exciting but not yet fully there that I think partnerships with industry and academia could enable. A big fulcrum there that is cool, though, is like, well, why lithium? Why not something else, like maybe sodium? And there's a lot of work going on with sodium in academia and in the startup world, where if it were possible to get sodium to be as compelling as lithium is, especially for grid storage, where energy density doesn't really matter, it's more about the life cycle of energy, the throughput energy through the battery pack. Maybe we do sodium for the grid, which like greatly reduces the need to scale lithium. These are the kinds of things that partnership between academia and industry can enable this 50% year-on-year growth of energy storage for all the ways in which energy storage can, decarbonize the grid and transport happen sooner, happen more facilely, I guess. Like ultimately, the current road of like lithium or bust is possible, very possible. There's plenty of lithium. It just would be great if there was just like one more entree at the table. So sodium might help, and other things like that might help.
Yeah, you will be happy to learn, actually Stanford right here. We have a number of faculty working together on lithium extraction.
Good.
From low concentration sources.
Yes.
Well, I think Steve Chu yesterday coming here and already mentioned that briefly. We have a project, we go to the extreme, extract lithium from ocean. Of course, that's 178 ppb, very low.
Yeah.
Going to the oil field, well, that's much higher. You go to 10 ppm level or higher, then becomes doable.
Yeah.
So there's a very strong team right here working hard towards that. It will be great to talk about partnership with industry.
Well, just one other thing.
Yeah.
On the scaling, and again on the raw material side, the other thing is, and maybe you've heard people talking about Tesla using something other than just nickel. Like, for sure, we're like equal opportunity cathode company. Like, whatever, seriously, whatever can be, sensibly mined and refined without undue environmental damage or social destruction, and is like reasonably available, and we're not doing crazy things in crazy places. Like, we're willing to entertain using, but it would be fantastic if we could get rid of the metal in the cathode. And there's some research efforts that are out there also to do kind of like graphite on graphite or other sort of non-transition metal cathodes, which would be fantastic. I encourage all of you, if you are an electrochemist or fancy yourself to be one day, to take that on, because finding a way to avoid having to mine and refine 300 to 500 terawatt hours worth of transition metals would be fantastic. And then you wouldn't need to go through the pain of, not that it's impossible, of recycling that either. I mean, you would still recycle that, but you wouldn't be having to go through these crazy synthesis steps that are part of these transition metal cathodes today.
Yeah.
Crazy is a strong word. It's doable. It's just, you wish you didn't have to.
So Drew, you touch upon recycling and circular economy.
Yeah.
I think to get to this several hundred terawatt hour, a circular economy is very much required, as you mentioned in our chat earlier today.
Yeah.
What do you think are the remaining innovation? When we think about recycling or repurposing, we think of it as a generally a understood process, it just has to be scaled.
Yeah.
Could you comment a bit on what's the missing innovations that we can still pursue?
Sure, yeah. Recycling is the end game for sure. So we get the 300 to 500 terawatt hours built. We get, let's say, 90 to 95% recycling efficacy. That means only 5 to 10% virgin material. And recycling, just as a total embedded energy and embedded cost way to get these resources is like an order of magnitude-ish lower cost and lower embodied energy. So it's a huge and obvious end game. We're doing recycling up in Reno at the Gigafactory, and we've got our approach to it. I think the areas where we're still developing and where there's still more opportunities, it actually is similar to what we just discussed. Like, how do we get lithium out of water,
Yep.
or like solutions more easily? But there's a couple other areas where it's kind of I don't want to say mundane, but it's like maybe not historically considered like sort of sexy area, but just like water treatment in general. Because if you think about different ways to go after the recycling problem, there's the way of like burn it all, and even if you burn it in like a low oxygen environment or whatever, like you're still burning it, which has its own like air side treatment challenges, or you're doing it with water and then you have water side treatment challenges. Either way, there's like kind of the nasties that you need to deal with. And there's more research required to sort of downsize the capital cost, improve the efficiency of those solutions. Some of them have a lot of overlap with the hydrogen, like the new hydrogen wave of like, how do we get hydrogen produced, which is like, how do we make electrolyzers cheaper? That's also in battery recycling as well. So there's a lot of overlap between kind of areas of the new economy that help each other. So yeah, electrolysis, water treatment, which tends to also include electrolysis, as ways to kind of get back out the pure materials that you need to start the process again.
Yeah. We have a little bit of time before we open to questions from the audience. Maybe let me just ask one more.
Yeah.
We have Robin sitting right there. Robin helped setting up Tesla China. We're thinking about now globally, the global supply chain geopolitical constraint. So what are the challenges problem Tesla is facing, how do you guys address that in terms of global supply chain whole thinking?
Yeah, I mean, wouldn't it be great if we could all just get along? I mean, yeah, there are plenty of difficulties associated with COVID, associated with policies that, you know, former administrations, future administrations are putting in place that do serve to kind of like, it's like kind of an undue burden on this, I think, like pretty existential threat need to accelerate the electrify everything movement. It is frustrating, but like all we can do is sort of our best to work around it. Ultimately, it does make sense for there to be a local supply chain for energy storage on every continent. And, you know, similar to every other new economy thing, China has very well, does a fantastic job of like investing in what is necessary to get the job done, whether it's solar or batteries or otherwise. And the rest of the world lets them do it, and you know, the industry around that sees that happening and sort of like follows the capital, and then you get what you get. I think there's no reason why China is the only place that battery materials are largely refined and synthesized today. Like, there's not a good reason, right? It just is where the capital has gone because of government intervention. You know, American manufacturing, European manufacturing, Asia, you know, Australia, it doesn't matter. Like, everybody can do this stuff. This isn't like nuclear technology that's held in lock and key and governed by a treaty. So everybody should be doing it. And I think with the general awareness, again, in the public psyche that this is coming, I expect more and more policymakers to be intentionally attracting local capital to do the mining, refining, the battery making locally, which I'm 100% supportive of. And Tesla has been doing it. I mean, we're putting money where our mouth is. Huge 100 gigawatt hour battery in Texas, factory in Texas with Cathode there. Same thing in Berlin. Like, we're in recycling in both of those places. Like, we're doing what we can do. Everybody is excited to do that, I think.
Let me ask a question on behalf of our students and trainees. In my decade at Stanford, I have now witnessed the transition from students and postdocs want to do cool science into doing science that matters, right? Because they see all these great opportunities for impact. Drew, can you maybe comment and maybe lay out for us, what are some of the capabilities or questions that you think academia is uniquely positioned to address that even well-resourced companies like Tesla can't get to? Something that we can uniquely contribute.
Yeah. I was saying this to you earlier. So when you look at what, you know, Tesla or any other company is struggling with as we sort of go from R&D, which is like not academic R&D, but like industrial R&D, to scaling and production, it's a lot of interdisciplinary problem solving that pulls together mechanical, electrical, manufacturing, you know, chemical, materials to solve, you know, challenging problems. The people on my team say they probably work on 2 to 3 doctoral theses worth of work a year, but they're not particularly like headline grabbing problems. And that's okay. Like, people are excited to solve hard problems. They feel great when they solve them. But it's, you know, like, this machine, the yield isn't what it should be. Why isn't it? Oh, okay, it's like because of the CTE mismatch of that and that over the temperature cycle of the process. You know, it's wobbling it by a couple microns. And like, okay, I finally figured that all out. Now I know how to design it out through like these mechanical changes. You know, that takes them like 3 months, and eventually they've solved that problem and the yield goes up by half a percentage point. Like, that's the kind of stuff. I think you know, reflecting on the ways in which academia can help the industry, it's really about accelerating the pace of iteration. If we think about what enables, you know, products to get better over time, or technologies to reduce in costs over time, or capital costs to go down over time, it's an iteration loop every time. Like, we're going to try these things because we think it's going to make it better, cheaper, more efficient, or whatever. And maybe they do. It'll take us a year and a half to like see if they do. And then if they do, it'll take us another year and a half to ramp them. So it's like a 3-year full cycle in industry for something like a vehicle or energy storage system or something like that. So how do we compress that time? I gave you an example of, finite element analysis is something that came out of academia as a way to accelerate the mechanical or electromechanical design of lots of things. Stress members in vehicle chassis or rockets. Will the seatbelt, pretensioner yield under the crash event? Will the frontal crash zone crumple in such a way in a crash so that people in the seats don't end up injured? That's all come out of academic FEA. And in particular, like I was telling you, William, you before, like finite element analysis for motors has, like over the past 20 years, has done amazing things for making electric motors more efficient. And that is a tool set that is working through the fundamental equations of the materials, Maxwell's equations, the everything that's associated with electromagnetism, and allowing you to predict the motor performance before you've even built it to really well, like within 1%. Think about how enabling that is. It shrinks the first 1.5 years to like 3 months. How do we do that with batteries? It doesn't work like that for batteries, really at all. You can do some stuff with some electrode modeling if you know everything about the materials in the electrode before you start. Or if you've already built the electrode, then you can like characterize it. But even that takes a long time. Because if you're thinking about a new material that's never been synthesized before, and it actually matters whether it's synthesized at a gram or a kilogram or 1,000 kilogram scale, oh man, now I got to build a 1,000 kilogram scale factory to know what the battery is going to perform like? That's like another 1.5-year cycle. So figuring out how to apply that mindset of like investment in analytical tools for the purpose of accelerating things like electrolyzers or batteries or anode and cathode materials will be huge if we can get those tools into the tool chain. Because 3 years versus 1.5 years is that much faster of an iteration loop and that much faster growth and reduction in cost and reduction in CapEx and energy and everything else.
Yeah, I think my student will be happy to learn about, you can get a PhD within 6 months if you work at Tesla pace. That's what I get out of your conversation. So after today's conference, get back to the lab. Let's get your PhD done, right? We have a few minutes left. Why don't we open up to audience for Q&A? Hamdi.
I like the way you put it with accelerating the pace of iteration. My question for you is, what do you think are the main scientific challenges to arrest aging of batteries? So if your battery can last 100 years, what would it take to understand aging, reverse it, arrest it? Is that something you're investing in?
Yeah. So the interesting thing about that question is that there's like this belief that people can make things that last forever. But when was the last time you looked at a house built in 1950 and said, everything in this house looks amazing? Right? Like,
well, I grew up in Jordan, and we have houses that are 300 years old. So,
okay.
So I'm not sure that holds.
Okay. Counterpoint,
Yeah.
argument. I understood. I think if we tried to make that same 300-year-old house in Jordan today, it would probably cost a little bit more.
A lot more. Yeah.
And that's kind of the point, I think, is, we need to get to the point where everything lasts a similar amount of time. And, the financial engineers that started making solar affordable kind of bet on the come that solar fields would be deployed and last 20 to 30 years. And they were kind of wrong. Because even though in the lab everything looked great, when it got out there were a lot of failure modes that they didn't understand. But eventually, with improvements in backsheet and sealant and all these other things that have happened over the years, they kind of last 20 to 30 years. Batteries, we can look at them electrochemically and we can, Jeff Dahn says 1 million miles and stuff. Yeah, sure. You can do all of that. But that's just in a controlled lab environment, the intercalation reaction, of like lithium shuttling back and forth across separator. It's not, does the battery system around those like nanometer scale things hold up for 20 to 30 years?
Yeah, but that's maybe where simulation can help.
Yeah, absolutely. And these are the things that we need to figure out. It's like, how do you maintain perfect sealing. You can't get any water inside the batteries, or they're basically done. So how do you maintain that over 30 years? You need to maintain the head pressure. Like you need to manage the gassing that happens in at least the liquid electrolyte systems within the pressure capability of the device. You need to manage the sort of like volume swell and everything else of the various materials involved through the lithiation and delithiation, so that you don't end up with any sort of material moving out of the way in funny ways to result in weak shorts over time. These are very hard things to simulate. There is work going on at Tesla, Vinit's in the back, trying to simulate a lot of this, and we're getting better, but we're definitely not at the point where like I can confidently tell you that the battery installation, for all that we know about it, is going to last as long as the solar installation. And by the way, it took them at least 40 years to be right about their predictions on the solar side. They were wrong for 20 years in saying it would last 30 years before they finally got it to sort of last 25 to 30 years. So we'll get there. And it needs to be done so that the same way that you deploy the renewable energy capital, you deploy the storage capital on the same financial engineering spreadsheet, and it's all on the same sort of replenishment time frame. That's where we need to get to for the grid storage side to be as low cost as it should be and can be.
Drew, can I ask you to look back? So, when you came out with the Roadster and the Model S, you probably had some internal predictions on when the battery would fail. And now you have the data.
Yeah.
How was your prediction at that time? Because you knew a lot less back then.
Yeah, we were very pessimistic. we were unnecessarily pessimistic about how long the batteries would last. Electrochemically, we were over optimistic on how long they would last for all the other reasons. So, we had water ingress issues at the battery pack level that had nothing to do with the cell that we had to learn about how to deal with. We had a lot of, there's a lot of electronics in batteries to monitor all the cell voltages and do all that stuff. And we had learnings about ways in which electronics can fail, and maybe whether or not they should be serviceable so that that's not a reason to scrap a battery. We had some learnings about, shock and vibration or thermal cycling that don't show up until you've been in the field for 10 years that had nothing to do with the cells. So honestly, looking back on it, the cells have outlasted our expectation. Outside of the cell has come short of our expectation. Yeah. And that's something that as sort of the design world sort of solidifies over, it doesn't matter whether it's a prismatic or a pouch or a cylindrical cell, like the way that you package that into a battery pack, as that kind of lands on a consistent structure, similar to what's happened with solar. Like if you look at a module today, you look at a module 20 years ago, it's very similar, basically the same construction. Those failure modes will be understood, and we'll be back to the electrochemistry being the dominant thing we need to do a better job understanding. We're not there right now, which is interesting. It's not what you'd think. It'd be like if the engine person was always asked, well, what about your piston seals? And the engine person was like, actually, it's always the exhaust system that fails first, which is kind of true, with engines.
So we are running out of time, but because it's very hard to get you, what if we extend a few more minutes? How is that? Yeah.
Works.
But let's do 2 quick questions, Gao Liu, and then I think Dan Riker raised the hand first, right? And then we got to get a lady. 3 questions to ask.
All right.
Yeah. But let's be fast.
So that's great to talk about the 3 terawatt we have to build, right? I think that's kind of like
300.
Right, 300, right?
Yeah.
And now we're kind of getting into like a planned economy, right? We know how much we're going to get there. Yeah. So, and we also know how much we want to build in the United States, right? So I want to ask actually a question regarding to the business side, right? What do you think is actually the things that prevent you from building factories, getting these things done? What are the critical things you think if we can change the policy that, there will be more and more factories being built quickly? So.
Yeah, the factories are not the issue at the moment, honestly. Like the permitting and construction timeline of a battery factory or a cathode factory that does the cathode synthesis, or even like the anode finishing stuff for the anode, it's maybe 2.5 years from like beginning the process to ending the process and ramping production. You could do it a little bit faster. It might take you a little bit longer, but that's really not the bottleneck on the 50% year-on-year growth. It's the fact that, there's enough lithium in Nevada to produce enough batteries for all of the vehicles in the United States. But the last mine to come online in Nevada took 10 years to get permitted. That is the bigger issue. It is that issue. It is the resource extraction timelines in most of the developed world, and most of the developing world now too, are just extended for some good reasons and some not so great reasons. And that's where kind of like the direct hand of government could help improve that, and it's not like there should be no environmental process. That's not what I'm saying. It's just we need to find a way to not have like 3 in a row, which is typically kind of how it works, where it's like you do one, and then like it's reevaluated again by another group, and then another group, and then like every step along the way, there's many, many opportunities for public comment and lots of thousands and thousands of pages to write. So that's the area where, it's not the factories. The factories are easy. It's the mining and refining that is slow, that needs to be accelerated.
Dan.
Hey. Hello.
I can hear you.
We can repeat the question, Dan. It's okay.
Yeah.
All right. You can see I'm not a technologist. Dan Riker, Stanford. So just like it's taken decades to develop solar panels that we get good performance, it's also taken decades to develop the solar shingle that combines a solar panel and roofing materials.
Yeah.
I was involved in the 90s, used to carry one around in my briefcase. You guys finally figured it out. I have a set on my house, and they're quite amazing. But I'm wondering how committed you are to that technology. Can you drive costs down? There's a very ugly story in the New York Times about Tesla and the solar shingle, and I'm really hoping you stick with it and turn this into a real product. 6 million roofs get replaced every year in the United States.
Yeah.
And if you really want to make solar roofing happen, it's not solar panels on a roof. It's the roof is both roofing material and solar.
Preaching to the choir with me. Lacey, my wife, was in the car with me earlier today, and I was like, that should be a solar roof, that should be a solar roof, that should be a solar roof. Look at that, like 50-year-old wood shake roof. It's a fire hazard. That should be a solar roof. So, yeah, we have a solar roof on our house. I think the thing that Tesla, it's kind of like a common ivory towerism kind of problem. Like, if you sit in a closed environment and imagine an ideal product for anything, you can like optimize the stuff that you do at the and like completely miss the forest for the trees and the stuff that you don't do. And so with solar roof, we spent a lot of time on the shingle and not enough time on like the stuff around the shingle. And when I say the stuff around the shingle, like there's a lot of perimeter flashings on a roof, a ton of perimeter flashings on a roof. You take a 2,000 square foot roof, there's like, 8,000 linear feet or something like that of flashing stuff. And that doesn't even include any of the obstructions and stuff like that, plumbing vents and kitchen fan exhausts and just so much stuff. So the engineering team spent a lot of time making that shingle awesome, and it's super easy to build and like not expensive at all, and not enough time working on making the roof job as simple as possible. And that's where the focus is now. I can't really comment because they're not responsible. I'm not responsible for the solar roof, and I'm not making the like product decisions. I can't really comment on how enduring is our commitment, but I can say that like personally my vision is and Elon has stated it very many times, and you've all heard it, is that every roof should be a live roof, not a dead roof. Wouldn't that be great? Isn't that how it should be? And like the tile, the thing that we're making is not the reason why we can't do that right now. It is not an expensive roofing material, and it generates plenty of power for what it is. So it's everything else about it. And in the same way that, you know, shingle roofs, asphalt shingle roofs didn't start out cheap, and now they are, like, it'll happen, is my sort of futurist view. Yeah, no worries.
So Drew will take last question from the lady, and then Will make the concluding remark. Yeah.
Great. Thank you, Professor Cui, to give me this opportunity to ask the last question for today. It has been a great day for today. Thank you. And also, Drew, welcome to Stanford. I'm a student from GSB. I'm an MBA student. So my question for you is, Tesla is an industry leader to develop the fast charge. So the battery charging time can be shortened a lot. But to my best knowledge, I don't think Tesla is very actively looking for battery swap, right?
Yeah.
So may I know why is that? Can you help me to understand it?
We sort of looked at kind of like if you imagine charging as a standalone business, like with profit and loss lines and OpEx and CapEx to make it go, that's what we evaluated when evaluating like swaps versus charging infrastructure. And kind of like when you have the swaps, you still need the charging infrastructure, but now you need the swapping infrastructure too, and the storage infrastructure for the swap batteries, and all of the like mechanisms to do those two other things. So it's just on a pure P&L basis to like provide the same function to people didn't seem to make sense. And you know, I'm responsible for Tesla supercharging actually, and we run it like a business, and it has its own P&L, and it needs to be profitable in its own right. And we look at all the costs, and you want to do the absolute bare minimum at the site to make the charging possible. And swapping is not the absolute bare minimum really at all. And if you look at some of our videos, like the pinned tweet on Tesla charging on Twitter, and I'm not a Twitter person, I'm just telling you. If you look at the pinned tweet on Tesla charging, there's a video of us building a supercharging station, like I don't know how many stall site in Florida. You know, it's like 4 days of work, and it's all wired up, and the last 4 days are like landscaping to make it look nice. That is what you can do with charging that you can't do with swapping. It's never going to be like that. Yeah.
Drew, thank you for concluding the day on such a high note. I'd like to, of course, thank everyone for listening and joining us for the day. I think if I were to sum up the learnings over the past 40 minutes, I think if I may, it is really about understanding the real bottleneck of a problem, no matter how simple or hard it might look. Go solve it, be practical about it. And I think what Tesla has taught us is we should be inspired to do better on every single process. And then it adds up really well. And I hope that message is also resonates with all of you. And on behalf of Stanford, Drew, thanks for coming back and sharing your learnings with us. Really appreciate it.
Yeah, thank you.
Thank you, everyone.